In the natural world, intricate ecosystems thrive on the interconnectedness of diverse species. Each organism, from the smallest insect to the largest mammal, plays a vital role in maintaining the delicate balance of the environment. Similarly, in the digital realm, we find a parallel universe of interconnected systems working together. This interconnectedness is what we call interoperability. Imagine a world where computers, software applications, and databases could seamlessly communicate and share information, regardless of their underlying technologies. This is the promise of interoperability, a world where systems work together in harmony, much like a well-conducted orchestra. But achieving this harmony is no easy feat. Just as a conductor must ensure that every instrument plays its part flawlessly, we must establish clear rules and standards for systems to interact effectively. This is where the concepts of syntactic and semantic interoperability come into play. These concepts are vital for unlocking the true potential of our digital world, enabling us to build more efficient, intelligent, and interconnected systems that can address complex challenges and improve our lives in countless ways. Syntactic interoperability can be likened to the grammar of a language. It focuses on the structure and format of data exchange between systems. Imagine two people trying to communicate, one speaking English and the other speaking Spanish. Without a common language, communication becomes impossible. Similarly, in the digital world, systems need to agree on a common syntax for exchanging information. This common syntax ensures that data is packaged and transmitted in a way that both the sending and receiving systems can understand. For instance, when you withdraw money from an ATM, syntactic interoperability ensures that the ATM's request for your account information is understood by your bank's systems. This exchange relies on standardized protocols and data formats that enable the ATM and the bank systems to communicate seamlessly, despite being built by different manufacturers and potentially using different underlying technologies. Syntactic interoperability lays the foundation for communication between systems. It provides a standardized framework for exchanging data, ensuring that messages are structured correctly and can be interpreted by all participating systems. However, understanding the grammar of a language is only the first step towards meaningful communication. We also need to grasp the meaning of the words being used. This is where semantic interoperability comes into play. Semantic interoperability goes beyond the mere exchange of data. It focuses on ensuring that the exchanged information is correctly interpreted and understood by all communicating systems. It's like ensuring that both speakers of English and Spanish understand the meaning of the words they are using, even if the words themselves are different. Let's consider an example from the healthcare industry. Suppose a hospital wants to share a patient's medical record with a specialist in another hospital. While syntactic interoperability ensures that the patient's information, such as name, age, and diagnosis, is transmitted correctly, semantic interoperability ensures that both hospitals interpret this information in the same way. For instance, the term diabetes should have the same medical meaning in both systems, preventing any misinterpretations that could impact the patient's care. Semantic interoperability requires defining shared vocabularies, ontologies, and data models that establish a common understanding of the data being exchanged. This shared understanding is crucial for enabling systems to interpret data correctly, reason about it, and make informed decisions. In essence, semantic interoperability is the key to unlocking the true potential of data exchange, enabling systems to move beyond simple data transfers to achieve meaningful collaboration and interoperability. In our interconnected world, systems often need to interact with each other without prior knowledge of each other's capabilities or the specific data they exchange. This is where the concept of context becomes crucial. Imagine you're traveling to a foreign country where you don't speak the language. You might use a translation app to communicate basic phrases. But what if you need to explain a more complex concept? This is where contextual awareness becomes essential. In the digital realm, systems need similar contextual awareness to interact effectively with unknown entities. This involves the ability to discover, understand, and adapt. Systems should be able to find other systems or services relevant to their needs. This might involve searching a directory, broadcasting a request, or relying on other discovery mechanisms. Once a system discovers a potential interaction partner, it needs to understand the services offered, the data exchanged, and the protocols used. This often involves querying the other system for its capabilities and specifications. Based on the discovered information, systems need to adapt their communication style, data formats, or protocols to ensure successful interaction. This might involve transforming data, translating between protocols, or negotiating a common understanding. Section 5. Real-world connections from Google Maps to traffic sensors. The principles of discovery and response handling are evident in various real-world applications. Consider Google Maps, a service we rely on daily for navigation. When you request directions, Google Maps doesn't simply access a static map. Instead, it interacts with numerous other systems in real time. Google Maps communicates with traffic sensors, GPS satellites, and even other users' mobile devices to gather real-time traffic data, road closures, and other relevant information. It then processes this data and presents you with the most efficient route, constantly adapting based on changing conditions. Another example is the interconnected network of traffic management systems in modern cities. Traffic lights, speed cameras, and electronic road signs communicate with each other and with a central control center, sharing data on traffic flow, congestion, and incidents. This real-time information allows the system to optimize traffic light timings, adjust speed limits, and provide drivers with timely alerts, ultimately improving traffic flow and safety. Section 6. A system of systems, the bigger picture. As we connect more devices and systems, we move beyond simple interoperability toward the concept of a system of systems, SOS. An SOS is a collection of independent, heterogeneous systems that collaborate to achieve a common goal, offering greater functionality and performance than the sum of their parts. Think of a smart city as an example. It comprises various interconnected systems like traffic management, public transportation, energy grids, water management, waste management, and emergency services. Each system operates independently but also shares data and coordinates with others to optimize city operations, conserve resources, and enhance citizens' quality of life. SOS can be categorized into 4 types: directed, acknowledged, collaborative, and virtual. Directed. A central system controls and manages the interactions between constituent systems. An example is air traffic control, where a central authority directs the movement of aircraft. Acknowledged. Constituent systems operate independently but are aware of each other and agree on communication protocols and data exchange standards. The Internet is an example of an acknowledged SOS. Collaborative systems work together to achieve a common goal, sharing information and resources dynamically. Smart grids, where energy providers and consumers coordinate to balance energy consumption, exemplify this type. Virtual systems temporarily connect and collaborate to achieve a specific objective, disbanding once the goal is achieved. Disaster relief efforts often involve the formation of virtual SOS, where organizations and resources are temporarily pooled to address the crisis. Section 7. SOAP versus REST, a tale of 2 protocols. When it comes to enabling interoperability, 2 prominent contenders often enter the ring: SOAP, Simple Object Access Protocol, and REST, Representational State Transfer. These architectural styles dictate how systems communicate and exchange data, each with strengths and weaknesses. SOAP, as its name suggests, relies on XML-based messages to exchange information. It's like sending a formal letter, adhering to a strict format and structure. This rigidity ensures reliability and consistency, particularly crucial for sensitive transactions like financial operations or healthcare data exchange. REST, on the other hand, favors a more lightweight approach, often employing simpler JSON or XML formats for data exchange. It's analogous to sending a postcard, concise, efficient, and flexible. This agility makes REST suitable for web services and mobile applications where speed and adaptability are paramount. Choosing between SOAP and REST is akin to selecting the right tool for the job. SOAP, with its robust security and reliability, shines in enterprise-level applications where data integrity is paramount. REST, known for its lightweight nature and ease of implementation, thrives in web services and mobile applications where agility is key. Section 8. Choosing the right tool for the job. Selecting the appropriate architectural style, whether SOAP or REST, depends on several factors, each influencing the decision-making process. Security. For applications handling sensitive data like financial transactions or medical records, SOAP's robust security features, often incorporating WS security extensions for enhanced encryption and authentication, make it the preferred choice. Transactions. When dealing with operations requiring atomicity, where multiple steps must be completed successfully for the entire transaction to succeed, SOAP's built-in support for ACID properties, atomicity, consistency, isolation, durability, offers a significant advantage. Complexity. For intricate systems involving numerous interconnected services and complex data structures, SOAP's rigid structure and predefined message formats can simplify development and maintenance, ensuring consistency and reducing ambiguity. Performance. In scenarios where speed and low latency are critical, such as web services or mobile applications handling frequent requests with relatively small data payloads, REST's lightweight nature and reliance on simpler protocols like HTTP often translate to better performance. Scalability. REST's stateless nature, where each request from a client to a server is independent of previous requests, makes it inherently scalable. This characteristic makes REST suitable for handling large numbers of concurrent requests, a common requirement for web and mobile applications. Section 9. The enduring value of interoperability. The ability of systems to interoperate seamlessly is not a technological luxury, it's a fundamental necessity in our increasingly interconnected world. Just as a well-coordinated ecosystem thrives on the interdependence of its inhabitants, our digital landscape depends on the harmonious interaction of its diverse systems. Effective interoperability transcends the mere exchange of information. It fosters collaboration, unlocks innovation, and paves the way for a more efficient and interconnected future. By embracing the principles of interoperability, we empower ourselves to address complex challenges, optimize resource utilization, and ultimately create a more interconnected and harmonious digital world. As we venture further into the digital age, the importance of interoperability will continue to grow, shaping the way we live, work, and interact with the world around us. By embracing the power of interoperability, we unlock a future where technology seamlessly integrates into our lives, fostering collaboration, driving innovation, and ultimately creating a more interconnected and harmonious global community.